All right, Chem 11, our next topic is average atomic mass. And today we're going to figure out why our chem class is smarter than all of those other classes that are out there. Anyway, average atomic mass. When we look at a periodic table, I have one right here, I can see a whole bunch of information for each of the elements that we've discovered, right? And on this periodic table, I take a look at an element like carbon. I can see two very important pieces of information about carbon. One is the atomic number. For carbon, it is 6. The other one is the average mass. I can see it here. So here's my atomic number, and then I can see my average mass right here, the average atomic mass for an element. So if I go to carbon, I can see that it's 6, and then for the mass, it's 12.01. So I'm just going to draw those right here. All right, little side notes. This is the atomic number. This is the average mass. All right. So if I look at an atom of carbon, periodic table, thank you, we'll see in a little bit. If I look at an atom of carbon and I look at the makeup of it, I can see that in that carbon, so if I look at a carbon atom, the number of protons, right? The number of protons, you guys figured out how to do this in grade 9, maybe even earlier. You just look at the atomic number. So the number of protons is 6. And then I know for every atom, the number of electrons has to be the same if it's an atom, right? Things change if it's an ion. But for an atom, the number of positive charges and the number of negative charges is going to balance out. So that's also 6. And then we also have neutrons. They have no charge. So I put a little 0 there by the end. To figure out the number of neutrons, I simply take the mass number, which is 12, and subtract the atomic number, which is 6, right? Because we know in terms of their weight, a proton is 1 atomic mass unit, a neutron is 1 atomic mass unit, electron is basically 0. They weigh very, very little. Their mass is almost negligible compared to the other subatomic particles, the proton and the neutron. So to figure out the number of neutrons, I take this. This says, hey, in the nucleus, there's 12 things, right? 6 of them are protons. That means the other 6 are neutrons. So this 6 and this 6 give me the 12. Well, what about this? What about that 0.01? Where does that come from? And of course, everyone wants to jump on and say, hey, it's those electrons. The electrons, you said, weigh virtually nothing, and 0.01 is way less than 12. That's for the electrons. And that's not true, right? The electrons do not contribute to this at all, basically, for all intents and purposes. So where does the 0.01 come from? Well, let's go into why my class is smarter than other classes. All right, so I'm going to erase this. I think you guys knew this stuff already, so I feel safe in erasing it. Let's say there was a quiz. All right, so I've got my class, all right? My class on the quiz, everyone scores 13. All right, maybe the quiz is out of 15. 13 out of 15, pretty good grade. Everybody else, they only got 12. All right, so the principal wants to get the average for the class. So there's two ways of doing this, all right? So the average of all the students that took the quiz. Everyone in the entire school took the quiz. So our chem class, we got 13 on the quiz. Everybody else in the entire school got 12. All right? There's two ways of calculating the average for this. All right? The simplistic way is to take 13 plus 12 and divide it by 2. All right? This is basically taking the two values and just finding the average between 13 and 12. Well, we know that's going to be 25 over 2, which is 12.5. Well, that is the average of 13 and 12. But if we look at it a different way and bring in the actual abundance, right, the actual number of quiz takers into it, it becomes a little bit different. So we will not be calculating average atomic mass like this, right? That's one way of doing it, but that's not accurate. Think about it like this. Our class has 25 people. 25 people made 13. Our school has about 1,600 students. That means 1,575 made 12 on the quiz. That's way more people that made 12 than 13. If we talk about the two quiz scores, this one, 12, is way more abundant than this one, which is 13. All right? So the average, because almost everybody in the school made 12 and hardly anybody made 13 except for us really smart people in my class, that average would be more like this. And you're probably cluing in now going, wait a second, I think I know where you're going, Mr. McDonald. So here's the thing. Almost everybody in the school makes 12. A few of us make 13. If I average that out in relation to abundance, a whole bunch of abundant 12s, very few 13s out there. So if I took the average would be just above 12 because almost everybody is 12. Carbon is exactly the same. There's carbon 12, right? That's the carbon we just talked about. It has 6 protons and 6 neutrons in its nucleus. But there's also carbon 13. Carbon 13 still has the 6 protons because protons determine your identity and they're both carbon. But it has 7 neutrons, right? This is an isotope, right? These are isotopes of carbon. And all isotopes are still the same element. It's still carbon. Carbon 12 and carbon 13 is still carbon. The only difference between them is the number of neutrons. That's the only difference. Carbon 13 just weighs a little bit more than carbon 12. So when carbon 12 steps on the scale, it looks down. Oh, I weigh 12. Awesome. Carbon 13 does that. It weighs 1 more pound or 1 more kilogram, whatever you want to measure it. All right? And it's because of the difference in neutrons. The number of electrons for each would still be the same, even though it doesn't really impact our talk. They would still both have 6 electrons, right? Because our positives and negatives for an atom are going to cancel. So the real difference is these neutrons. All right? So let's bring that back to our quiz. This is like saying tons and tons of carbons are out there. When you go to the mall, when you go to the Jays game, when you go to the hockey game, when you go for a walk, you go to the park, you go wherever it is you happen to go, and you run into all these carbons, almost all of those carbons are carbon 12, right? Every once in a while, though, you're going to run into a carbon that is carbon 13. Like, hey, there's a carbon 13. You don't see that very often, right? 1 out of every 100 or so, right? So you run into 100 people in a day, 99 of them are carbon 12. 1 out of that 100 is going to be carbon 13. So if you took the average of that, it's 12.01. So this average tells us that the bulk of carbon that is out there is carbon 12. Very little of it is carbon 13. And I can tell that because the average is just barely above 12. If I look at another element, right? For example, if I look at sodium, sodium's average mass is 22.99. What does this tell us about sodium? It tells us that the bulk of sodium is 23. Almost all the sodium is 23. but the average is just below 23. So it means every so often I'm going to run into a sodium that is 22. And that drops the average ever so slightly because there's not a whole lot of sodium 22. There's a ton of sodium 23. So that's what these average atomic masses kind of tell us. They give us an idea of the proportion or fraction or abundance of each type of isotope. All right? So the 0.01 comes from the fact that there is a little bit of carbon-13 out there. It is not 0.01 for electrons. No, no, no. All right? Now, so let's calculate average atomic mass. There are two pieces of information that we have, all right, to calculate it. I need the relative atomic mass of each isotope for the element. All right, so for carbon, I would need that would be like saying, okay, one form of carbon is 12, that's the mass of that isotope. The other isotope is 13, that's the mass of that. All right? The relative atomic masses I will always give you. All right? Those will be given to you or provided to you in a table probably if I do a question like this. And you will have to do questions like this. All right? The other piece of information that I need, so I need that. I will also need the fraction or abundance. Now we're going to need this. If I'm given this, I got to turn that into that. All right? So an example for our carbon, right? Carbon 12, its abundance is 98.89%. Abundance is given as a percent. And we don't want a percent in our calculation. Fraction is given as a decimal, right? So what I do is I divide this by 100% and I'll get the decimal for it. All right? So I think in grade 9 math, maybe even in elementary school, you turn percents into decimals and all you always do is divide it by 100%. So if the question gives you abundance in percentages, we have to turn it into fraction. If the question gives you fraction, don't touch it. It's ready to rock and roll. You just use this number right here. All right? Or whatever the fraction is for the element. Okay? So we need these two pieces of information for each isotope. I need the relative atomic mass, and then I need the abundance or fraction. And if I'm given abundance, turn it into fraction. All right? So let's do a question. All right? And I'll give you an idea of what we're going to encounter here. Chlorine. Chlorine has two isotopes, and we're going to figure out the average atomic mass given the information. So a sample of chlorine was found. They ran it through a mass spectrometer, a machine we'll talk about in a later lecture. And here's the data they got. One form of chlorine is chlorine 35. All right? So the relative atomic mass is 35. Relative atomic mass. That was one of the two things we had to be given. So 35. Another form of chlorine that they found in that same sample, like I said, in a block of carbon, lots of the atoms are carbon, but there'll still be some carbon-13 in that same block. They aren't separated. They all mix and mingle around, just like people do, okay? So the other chlorine that they found, oh, these should be L's. The other chlorine had a mass of 37. So it had two more neutrons in its nucleus. The abundance given by the machine, and that's in a percentage, for chlorine 35, 75.77% had a mass of 35. In that same sample, the other 24.23% had a mass of 37. All right? So here's our information. We can now calculate the average atomic mass of chlorine. What I'm going to do first, though, is, like I said, I'm going to change this into fraction. So I'm going to divide that by 100, and I'll get 0.7577. I'll divide this by 100%, and I'll get 0.2423. All right? So I simply put these numbers in my calculator, divide by 100, it gets rid of it. I pretend it's 100%. That'll cancel out that sign. There's my fraction. So the info I need is this and these numbers here. All right? So what we're going to do for chlorine to figure out the average atomic mass is average atomic mass. Now this is the formula, and I'll show you kind of how it works. We're going to go to our first isotope, and we're going to take the relative atomic mass of isotope A, or form A of the element, and we're going to multiply it by the fraction of A. And then we're going to add to that. So we're going to add it to another bracket, the relative atomic mass of isotope B times the fraction of isotope B. Now, if there was a third isotope and a fourth, I would add relative atomic mass of C times a fraction of C plus the relative atomic mass of D times. So you get the idea. Every isotope gets one of these brackets. So A and then a B. If there's a third isotope, say for example, chlorine 38, I'd make a third bracket with relative atomic mass C times fraction of C. You guys get that, no worries. So, average atomic mass. Now, if I sub in my values, for my first isotope, my relative atomic mass is 35. I'm going to multiply that by my fraction. Common mistake, people putting this in. Make sure it's in fraction. So 0.7577 plus, I'm going to put this next bracket in here, the relative atomic mass of my B. So this was my A, this was my B. B was chlorine 37. I'm going to multiply it by the fraction of that, so 0.2423, and I'll bracket that off. The next thing I'm going to do is I'm going to take my calculator, my trusty Dollarama calculator, Dollarama, one of the best stores on earth, and we're going to multiply those. So 35 times 0.7577 equals 26.52. Plus our second bracket, I will do that as well. 37 plus 0.2423 equals 37 times 0.2423 equals 8.97. All right. The next step is to add these two numbers. So we're going to add the two numbers. So 26.52 plus 8.97 equals 35.49. Now, if I look on the periodic table, right? If I look at the periodic table for chlorine, it's right here. And its average atomic mass is 35.45. So that's very close to this. It means in this sample, right? I grabbed this data just off an example. In this sample, there's a little bit more chlorine 37 than there is in the average sample. That's all. But if I got a number like 50 something or 12, that tells me I messed up somewhere. So for chlorine, I can kind of cheat, go to my periodic table, see what that average atomic mass is, and then my calculation should come up pretty close to it. And it did, right? 35.45, 35.49. It's pretty much the same thing, all right? And each sample will have its own little unique variations on average atomic mass, all right? So that's that. I'll do one more for you as well. So if you're writing this down, pause the video, get it down. I'm going to erase this. Our next example, we'll do one for carbon. All right. So carbon, a sample of carbon was found. And carbon 12, its relative atomic mass was, well, 12. And then there was carbon 13. Its relative atomic mass is 13. In this sample, the abundance was found to be, for carbon 12, 98.89%, and only 1.11% for carbon 13. That kind of sounds right when you think about it. We talked about carbon saying, hey, pretty much everyone out there got 12, but a few of us got 13. This sample holds true to kind of what we already know. So we'll call carbon 12 form A, carbon 13 will be form B, and we'll get ready to go. All right? But before we do, what do we have to do? Well, I need this, and I got it. I need that sorta. I have to change it to fraction. So I divide by 100%, and I get that, and I divide this by 100%. Here is another common mistake. 1.11 divided by 100 moves that decimal 2 places. So it actually looks like this. But I will get this turned into that so often, right? This is 11%. That's 1%. They only move the decimal in front of the number. They don't remember to move it twice. So that decimal was here at 1.11. 1, 2, right? Divide by 100 moves the decimal twice. So please be aware of that. That happens way more often than it should with, single digit percents like 1 point something, right? So my fraction is correct here. So I'll do my formula. Average atomic mass equals the relative atomic mass of A times the fraction of A plus the relative atomic mass of B times the fraction of B. So I show my formula. Just like physics, we got to show formulas. And now we'll do the solution in red here. So my first bracket, the relative atomic mass of form A, I said A was going to be carbon 12, so it's 12. Times the fraction, which is this, not the percent, right? That, and then we'll add that to the second bracket. So I'll put my second bracket here. The relative atomic mass of form B, that's carbon 13, times the fraction, which is a 0.011. And then I'm going to solve for each bracket. So again, grab my trusty Dollarama calculator, and 12 times 0.9889 equals 11.87. That's my first bracket. And then 13 times 0.0111. And for this one, I get 0.14. I add those two numbers together now. So 11.87 plus 0.14 equals, guess what? 12.01. All right, a little bit of math magic there for you. Anyway, that checks out. I go to the periodic table and go, oh, look, it's exactly the same. right? The chlorine showed a little bit of variance, and different samples will do that as long as as long as it's a little bit. This one was bang on, so there you go. Anyway, on the D2L page, I'm going to put a worksheet with several of these problems on it. Give them a try. Very, very simple, nice, easy math to get us into the quantities unit. Very applicable chemistry to future jobs if you are in the chemistry industry. This next unit, quantitative chemistry, is chock full of all kinds of great examples of things that you would need to do in everyday life. So this is one of the first ones that we're doing, one of the first calculations. So nice and easy peasy to get you going. Anyway, thanks for listening, and we'll see you soon. Bye-bye.